So hello again. In my first video I had a quite extensive first look at these SBR10UU linear bearings with the accompanying SBR10 supported guide rods. That video turned into quite a lengthy rant, but well, if you're interested, there's a link down below in the description. And yeah, well, now I have these things, and since I wanted to build a CNC machine, using them, I wanted to find out how much load they can actually take. And in my first video, I already suspected that they kind of have their weak spots, since especially the SBR10UUs have only 1, 2, 3 rows of balls in the bearing. What I was especially interested in was how much force can they take from different angles of attack. And because of their construction with only 3 rows, I suspected that there would be especially bad at taking force that was pushing them up, that is, force that's pulling on them. And well, I found to call it a weak spot is kind of an understatement, a big understatement. But anyway, I went ahead and did a little bit reverse engineering of these things, because I couldn't find any information or drawing in that regard, technical drawing in that regard, on the position of the rows of balls, etc. And then I did some static calculations, and in this video I will yeah, simply let you follow along through my process, how I derived at my results. And we will first do a little bit of reverse engineering, and then do a little bit of static analysis. And no, we won't use a calculator, we won't use formulas. All we use for that kind of static analysis is, yeah, a triangle ruler. That's all what we need. Yeah, so let's start. Put that away for a second and have a look at the actual data sheet. So in the data sheet for the SBR linear bearings, you have at the very last, not very last, almost last column, you have some information called basic load rating. And this basic load rating, you have 2 different numbers. You have, for once, the dynamic load rating in newtons, and called CN, and the static load rating, CON. And you see these SBR10s, sorry, they have a dynamic load rating of 372 newtons and a static of 549. So what does that mean? Static load rating is basically the load the bearing can take when it's not moving. That is, the SBR10UU can force directly coming above, when it's not moving, of 549. If it's moving, or while it's moving, it can only take a force of 372. Of course, if you build a CNC machine, you will always go for the dynamic force, 372. Because, I mean, let's suppose this is your table axis. You move your table while you are pressing down with the tool. Yeah, so how did I went about reverse engineering these things? Yeah, trying to measure inside here was completely impractical. So I basically took a close-up photograph of the bearing and tried to align the axis of the lens exactly with the axis of the bearing. And I checked how good I was at that by drawing two circles into the picture, outer red circle and the inner blue circle, and checked how good the centers of the circles lined up. In a perfect world, they would be line up exactly, but well, that's good enough for me. Next thing I did, I drew lines along the rows of balls. And then what was left to do was to measure the angles. And of course, this is exactly the top, and I tried to align that as perpendicular as possible. This would be our 0 degrees or 90 degrees to the top surface of the bearing. So I assume, rounding up and down the numbers a little, that the angles between the rows of balls are 90 degrees. Oh, I will just assume that. I mean, here I got 89 degrees, here I got 91.6 degrees. And that the angle between the middle row and the actual bearing 0 degree is about 20 degrees. Yeah. And from that, I started my static calculations. Sorry, not calculations really, but drawings. Yeah. What is a static analysis, or what is static analysis or static calculations? As I said, this will not be a 101, just some principles. Basically, in a static analysis, you want to find out how the forces has to cancel out each other, or are in equilibrium, such a nice word, so that nothing moves. Let's say you play tug war, and this is our rope. We have two teams, right team and left team. How strong does each team has to pull that the rope is not moving? I mean, that's trivial. Each team has to pull at exactly the same force. So that's a trivial problem. Let's go to a little more complex problem, but it's, well, it's still basically, it's a basic technique of static analysis, and it's called a force rectangle. So instead of a war of tug war, we do a little push war. And let's say we have a table here, and yeah, daddy is pushing from this side, mommy is pushing from this side, and you see there's no way the table won't move, but now we place the child at that corner of the table and have it push too. And you see, I can adjust the forces so that there is no movement. And if we draw that, looks something like this. I have a table, and then daddy is pushing from this side, and the arrow is basically represents the length of the arrow represents the force daddy is pushing. And then we have mommy pushing, and we don't know how strong she's pushing. And we have the son pushing from here, and we also don't know how strong he's pushing. And basically what you are allowed to do in static analysis is, as long as these forces line up in a single point, okay, you are allowed to move these force lines in parallel and make a triangle out of it. So basically we can take that force line and move it here in that direction, and we can take the green one just parallel to here, pushing in this direction, and then you basically have your result. Here would be the end of the blue. To cancel out the force of the daddy, we need that much force from mommy and that much that much force from the son. That's basically the force triangle in static analysis. And yeah, you can do it with formulas, but you can also do it with a triangle ruler, as we will see. So let's go back to our graphic here, and yeah, put that into a more abstract form. So in the middle we have our guide rod, and we have our three rows of balls. That one, the blue one, and we have actually third one. Let's make that pink because we don't really need it at the moment. And these 3 rows of balls are basically in a 90-degree angle to each other. And I'm trying to be as exact as possible as one can be. So, and now we have, we remember the picture, 20% offset, but yeah, since I made that line upright, I have to turn that a little bit. So 20% offset would be our perpendicular line for the bearing. That is, yeah, I have to turn that a little bit. Our force coming directly from above. And at these 20 degrees, I will draw a line in red, if I find it. With a length of exactly 20 degrees, yeah, of exactly 100 millimeters. Okay, so I simply say 100 millimeter is 100%. That's the 100% of the, yeah, in our case, the dynamic load given in the data sheet. And, well, you remember the force triangle, and I've chosen the same color for a reason. To draw out the load, this blue and this green row of balls can take, the pink doesn't matter right now, we simply have to draw some more lines. And let's start by taking the blue line, which would go along here, so I can go parallel, draw parallel line up here in blue. And we also, and we don't have to move it parallel because it's already at the center, and the green row of balls exerts a force until here. So there you have your force triangle where all forces cancel each other out. So this is 100 millimeter. That is basically the maximum force for basic load, perpendicular load, again, perpendicular to the top of the bearing, given by the manufacturer. And this here are, say, 94 millimeters. So this is, that bearing takes 94% of that load, and my blue bearing will take 34% of the load. Now you can simply assume that 94% of the load given in the datasheet is the maximum a single row of balls can take. So if we want to know how much load the whole thing can take from another direction, we just have to draw a lot of triangles. And since this is rectangular here, it's really quite simple, because you simply take the maximum length, 49 millimeters or 49%, for each bearing. So now I get the pink bearing out here to 94. And the blue bearing goes out to, let's see, 94 again. Well, you can do this in parallel for the top. .94. The green one goes here. 94. The green one over here. 94. And the pink one at the top, 94. So, and if you want to know how much force can that whole bearing take from a different angle, you simply draw in the line of attack, and we cannot exceed on a single bearing the 94%, so wherever that line is crossing here, to complete the force triangle, wherever that line is crossing here, any of these outlines, that will be the load that can be taken from this direction. And you see here we already get 112%. That is even more than the basic load rating, which is good. And of course, if we do a diagonal here, there we can take the maximum force. But I've put this in a, well, nicer form. And in a drawing program, it's also a little bit more exact. So here we have our 94%, our force triangle initial one that I use to determine how much one roll of balls can take at the maximum from the 100% load rating from the vendor. And here you have your different angles of attack, and well, you could measure it. It goes up to 133% if it's diagonal. But if you use the bearing really in an engineering way of sense, and you're not sure where your angle of attack is, you really have to downgrade the whole thing to the minimum, which is 94%. And this would be this line. I have another drawing where I put the bearing, it's at a 20 degree offset in perpendicular orientation. And here you see what I meant with weak spot. So basically we cover 180 degrees. Any force that comes from behind that point cannot be taken by the bearing. Yeah, I mean, it's easy to see. It will shove the bearing, the bolts away from the bearing, and you would end up riding your bearing between the guide rod and the bearing housing instead on the bolts. But interestingly, even a force that comes from 90 degrees, exactly from the side to the bearing, at least for one side, that is true, doesn't work. It does not work. It will push your bearing off the guide rod, and you will ride the bearing on the housing. From the other side, obviously 90 degrees, it's okay. Yeah. So, where will I go from here? So, first of all, normally you use two sets of bearings in parallel in a CNC machine, in a typical CNC machine. Maybe this will get us out of the situation, and maybe there will be a second video of static load analysis of SBR10UU using two bearings. Maybe. But first I will do, and this will be a series of videos, static load analysis of my CNC machine. And yeah, if you watch that, you will learn a little bit more about static calculations and static analysis. I will keep the math to an absolute minimum. As I said before, it's not my intention to do a 101 on that subject. And, well, hopefully after a while we can actually build something where we are quite certain that it won't self-destruct the first time we power it up. Yeah. Thank you for watching, and hopefully you will follow this series.